All right. So today we'll be talking about the key value database that we use for Sybase. This is used to store all the chain data plus other, pretty much any data that needs to be stored for the blockchain. So at the base level, we have a key value storage. It allows keys up to 190 bytes and values up to 16 megabytes. Both the keys and the values are encoded as octet strings. So this is just the low-level interface that we'll be talking about today. It's up to higher level layers to encode objects or structs in an appropriate way. So the basic operations that we have are upsert, remove, and get. The root here holds the entire state of the database. Notice that the modifying operations, upsert and remove, take a root as the parameter and return a new root that represents the new state. They don't modify the existing state. This is important because it means that the write operations don't interfere with read-only operations. A read operation can have its own root and it can access a single consistent state, and it doesn't have to worry about writers changing that state out from underneath it. When we modify the state, the parts of the state that are not changed are shared with the old state to avoid making a lot of copies and blowing up memory usage. In addition to the regular blob values, you can also use another root as a value. We use this to store multiple versions of the chain state in the database. So for instance, you can take the state associated with a particular block and attach that to the block ID to allow fast fork switches. Using roots as the values also allows us to partition the database. For instance, the block log, event log, and service tables each live in a separate space. That, in theory, could be emulated by using a prefix to the key, but we do this enough that having a special case to handle this makes sense and makes our lives a lot easier. So for concurrency, even though the interface for modifying the database is purely functional, under the hood, the implementation actually moves data around a lot. So in order to protect that, we have to create a read session or a write session to wrap it that looks a lot like a read-write block or a mutex. Read sessions and write sessions can run concurrently with each other without any problems. So the main data structure that we use to implement this is a trie, which has 64 branches per node. The key is converted from octets to 6-bit chunks. That's the reason for the odd limit of 190 bytes, because that allows the number of 6-bit units in a key to fit in a single byte for encoding. The size of each node is variable because the node only stores pointers to the children that actually exist. So because the nodes are usually fairly sparse, that saves a lot of space. It does mean that you can't really add or remove children from a node, but that's not really a problem because we usually don't modify nodes in place. Instead, you just build a new node. So memory is allocated from a number of bins. There are 32 to 64 bins. Whenever we run out of space, we add a new bin to the end of the file. If we've already reached the maximum number of bins, then we double the bin size and merge adjacent bins, dropping back down to 32 bins. For small objects, there's also a cache, small being defined as less than 1 page. So small objects are copied to the cache when they are accessed, which improves locality of reference and reduces fragmentation. And that allows us to store data that is not frequently accessed on disk while keeping keys and values that are accessed frequently in memory. In order to allow us to copy objects around, the pointers that are stored inside the nodes are actually indexes into an array of pointers. When we need to move an object, we first copy the object to its new location and then update that one pointer rather than having to track down every single pointer everywhere. So bins are garbage collected using a background thread. we always keep at least one bin empty so that we can allocate without blocking. When we need to free a bin, we choose the bin that is least full and move all its objects out to make it empty. And the system is designed so that if a process crashes, the database will be left in the last committed state. But if there's a power failure or a hard shutdown, the database can be corrupted. This is because we're implementing it using atomic operations and relying on the system to flush pages to disk. The way the data is structured doesn't make it very easy to use something like fsync to force data to be written to non-volatile storage. So it's not really feasible within this design to make it survive a power failure. So that's the main limitation. Any questions?